All right. Okay, so we continue again with the second part of this objective today. So the second part will continue with the lecture lah, for the introduction of the control engineering tool. So let's say if you have any question throughout the session, so you can ask me. No problem with that. Okay, so we go to the introduction. So definition of control system, I believe you already understand what is a control system. However, I would like to highlight again what is a control system. A control system consists of subsystems and processes. Okay, so in this control system consists of two things, subsystems and processes, or plant we call it, or system. Okay, assemble for the purpose of obtaining a desired output. So this is the desired output location with desired performance. Give a specific input. So if you give the input and then you have the desired response, then you must have the actual response lah. So in order to get the actual response, it depending on the control system. So if the control system is good, then you will get the actual response with no error lah. So however, if the control system is not so good position, so you need to modify the system by implementing some control design. If you still remember that you did in control 1, you put PID controller in order to improve the output performance lah. Okay. So this is example of processes, plants, or systems. So this is a motor, a DC motor to spin the propeller. Okay, so this is a simple system, and the system also can go to advanced or complex system such robotic arm, such as Segway, such as this thing lah, for the antenna controller. Okay, control system. So I think according to the previous semester, you focus on two types of the system, electrical and mechanical system. Okay. So in this semester also it will be same. You will focus on the same system, electrical and mechanical system. Okay. All right. So what you did before in control system, the system can be represented in a block diagram. So let's say if we have this kind of the system, this system you can convert to this block diagram. So you can see that there's a desired azimuth angle here, and then you have the output azimuth angle. Okay, this one. So it's similar to this slide. If you feel input and output, in the middle will be control system. Same thing. We compare to this part, input, output. The in the middle is a control system. The control system, the definition consists of subsystems and also processes. So this is what we call subsystem and processes. Okay. All right. So according to the previous semester, you have this kind of block diagram, then you need to convert to the transfer function. Okay. So you already learned this thing, this process, this modeling process, transfer function from the block diagram. Because, however, before this, the block diagram is coming from the system. Okay. According to the example from this antenna control system lah. Okay. However, in this semester, you will convert this block diagram into a state space. So this is state space. When I talk in the synopsis about the state space, there are 3 times in synopsis repeat the word of state space. So this is the state space. The state space is an equation. Okay, equations. So if you can see that the difference between control 1 and this is control 1 and control 2, this is this block diagram. The block diagram is or the system is modeled to transfer function for control 1. For the control 2, the block diagram is modeled to a state space form. Okay, so if you can see that, what is the difference between transfer function and state space? If you see this equation, what can you see? What is the difference? If you can see that, I give you a hint. The domain. Anyone would like to try? The domain.
Time domain.
Time domain for the
State space.
For the transfer function,
Frequency.
Frequency domain. So you can see that in this case, you for the state space, you not need to convert to the Laplace, is it? You can use directly from the system, and you can obtain the equation straight away from the system without need to convert the system to the Laplace. Okay, so this is the state space lah. However, there is a connection between transfer function and state space. So it means that you can convert from transfer function to state space, and also you can convert from state space to the transfer function. Okay, if you have a new one, so don't forget the old one. Okay, so we can connect them together lah. So this is conversion process. So you will learn this thing. So firstly, what you will learn is you have this system, okay, and then you convert this system to a state space equation. After you convert to state space equation, then you can convert the state space equation to the transfer function, and also from transfer function to state space. Okay, so why you learn state space? Why you don't? Why you just learn the transfer function only? Okay, why we need state space? Okay, a state space also called a modern technique. So you can see this is a modern technique compared to the transfer function. Transfer function is a conventional technique. So you must know the conventional, and also you must know the modern technique. Okay, for the control. So if you know everything, so hopefully you can do well lah. For your controller design, if you are working in the industry, or to be a researcher student or master or PhD student. It's a unified method for modeling, analyzing, and designing a wide range of systems. This is the keyword, a wide range of systems. So the state space also can be used in nonlinear system. So if you still remember, in control 1, you just learn about linear system only, not nonlinear system. Okay, so that's why in this course, Dr. Siti Mahanis will teach you non-linear system. And then it's applicable to time varying system, okay, and applicable to multi-input and multi-output system, and easily tackled by the availability of advanced digital computer. So it means that if you have the state space, so it really easy if you want to integrate the system with the computer. If your system already converted in the state space form compared to the transfer function. Okay, so this is the advantages of the state space. So you can see that this is an example of the MIMO system, multi-input, multi-output. So this is easy if you use a state space. So let's say if you are using transfer function, It's really, really complicated. Okay, compared to the state space, if you are using state space to handle the multi-input and multi-output system, it's quite easy. Okay, so in control one, this is the kind of the system you learned: single input and single output system only. If you still remember lah. So you only learn about single input and single output. For the state space, you will learn up to multi-input and multi-output system. Okay, so conclusion for chapter number 1. Okay, so in this chapter, you will learn about, firstly, the state space structure. Okay, and then after that, you will do the modeling of the dynamic system. The dynamic system is mean that modeling converge. Okay, dynamic system is the electrical and mechanical system in this course lah, to a state space form. Okay, and then number 3, in this chapter also, you will learn about the signal flow graph of the state equations. So these words you still not familiar with that. So hopefully by the end of this in chapter, you will understand all the words here. And finally, you can do the simulation on the model system. So it means that you do the modeling and then you can convert to the signal flow graph. After you convert to signal flow graph, you can take the signal flow graph and transfer to the MATLAB Simulink. Okay, and then you can see the output performance of the model system. Okay, so the main outcome of this chapter is that you can work independently to simulate a system when you are only given a system such as RLC and the spring mass damper system. So I just give you a circuit, and then after that, you can work independently by converting the circuit into state space. After that, you transfer to the MATLAB Simulink and see the results. So this is the thing that will be covered in your lab 1. So let's say if you can do this everything, so you are okay with this chapter. So let's say if you are stuck at this modeling part, so I think you will be troubled lah, in order to get the signal flow graph and also to do the MATLAB Simulink. So it will be trouble for your lab 1. So let's say if you can do the signal flow graph only, I believe you can proceed, transfer to the MATLAB Simulink easily. Okay. So before proceed, do you have any question? Are you clear with this chapter number 1, direction, what we want to achieve?
Clear, Dr. Clear.
Alright, yeah. So that's really important lah. As long as you understand our target, then we know our direction or our path lah. That's really important. Okay, and then after that, I will share my screen again. Okay, so we go to the first one. Learn about the state space structure. So we focus on the first part. Okay, so we will follow these numbers in order to do our checklist lah. So after we finish the state space structure, then we go to the modeling. After this one, we go to signal flow graph, and after that, we do the simulation of the model system of MATLAB Simulink. So we go for the first topic in this chapter. Okay, so this is the state space structure. Okay, this is x dot t. We call x dot equal to ax plus bu. This is the number people say about the state space equation. We didn't say x dot t equal to axt plus but. This is not the common way we say about this equation. We just say that x dot equal to ax plus bu, y equal to cx plus du. So what is x dot? What is a x, b, u, y, c, d? Okay. So this is the definition lah. Definition for all the parameters inside the space equation. So x dot is a derivative of the state vector. So you can see the vector, 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 vector. So this is the direction lah, vector. Okay. X dot t also we call dx over dt lah. This is the normal way. Okay, we write. However, we can put the short forms with the x dot t. Okay, derivative of the state vector. Xt is a state vector, so it means that xt is a state vector. So x dot t, we just need to do the derivation of this state vector. Okay, and then yt, the common symbol y also always refer to the output vector. U also is common symbol. U also always refer to the input of control vector. A is a system matrix. B is an input matrix. C is an output matrix. D is a feed-forward matrix. So in this case, in order for you to survive for the chapter number 1, you must know how to solve the mathematical equation of the matrix. So matrix is really important in control engineering too. Okay. So you must know how to do the inverse Laplace. You must know inverse matrix. Everything lah. You must know how to find the adjoint of the matrix. You must know how to find the determinant of the matrix. So this is how you want to cover or you want to survive for this chapter. Matrix, mathematics. Okay, so this is an example of a state space structure of a RLC circuit. So let's say I give you this kind of circuit lah, RLC circuit. So normally this example, this is the form of the state space. So from this circuit, you can do the modeling and convert this circuit into this state space form. So you can see that this is x dot here. We do comparison, and then this is the matrix A. This is the matrix A, and this is xt, and then this is a B, and this is the U, input. So you can see that input U refer to V, this one. This is also always referred to the input lah, kan? Input voltage source. And then after that, the state vector. If you refer to the previous slide, xt refer to the state vector. Okay, in the state vector here, xt nominated by I current, V voltage. Current and voltage. Okay, and then after that, for the matrix A, you can see that negative R over L, minus 1 over L, 1 over CO. So you can see that this is the components of the system. Resistor, inductor, capacitor. Resistor, inductor, capacitor. So it means that this thing, if I give you the numbers, R equal to 2, L equal to 5, C equal to 3. So if you replace every here, it will be a number lah. Number. Okay, so this one won't be any number, so it will be staying VC, and this also will be a number, a set of number, and this still V. Okay, so you can see that the matrix A, B, matrix C, and matrix D will be a set of matrix number. Okay, so in order for you to convert this kind of circuit to this state space equation, you must refer to this table. For example, to get the state space structure according to the previous slide, the figure below is required. for electrical system modeling. Okay, so for the capacitor, you can see that the voltage, this is the equation. Okay, and then for the current C, this is the equation. Okay, this is equation. For the resistor, V equal the voltage, because we just need to refer to the time, the T domain, because state space in time domain. So we just need to refer to the first two column. Okay, the first two columns, voltage, current, voltage, current, voltage, and current. So for the inductor, the Vt, this is the formula, L dit over dt. And then for the current, 1 over L, derivative integration of the V tau d tau. Okay. So I want to ask you a question. Okay. You can see that in this state space only have the x dot parameter, x dot parameter. So can anyone tell me what is this x dot parameter that you can find in the first two column? Okay, you have these two capacitor, you have these three the components, capacitor, resistor, inductor. Can you see what is the x dot you can get from these two columns? Maybe I can call name by name. Ahmad Aiman. Ahmad Aiman bin Ahmad Asri. X dot. I go to the first part. X dot is the dx over dt. You need to derive a parameter of x in here. So C. In this. Aiman?
Ya, Doktor.
So what is the x dot component from these two columns? You can see. You just compare.
dV over dt.
dVt over dt, that's correct. So you have the dVt over dt is your x dot, is it? Okay. And then is there anything I would like to call Arimugan, sorry. Arimugan, are you there? Arimugan. I can say that you are absent lah. Arimugan. Oh, let me see. Is it in chat section? What's the question again? I think I already repeat the question about few times, Arimugan. Okay, I repeat again the question, so I can expect you do something else lah during the lecture. However, this is my theory only, but if my theory is wrong, I'm sorry for that. Okay, the question again is, this is the x dot here. Okay, this is a state space structure. So based on this table, what is the x dot you can find from these two columns? Arimugan. Okay, Arimugan, Can you answer the question, or you would like to pass, or you still don't know the question? Tak lagi. Cuma sebab dia tengah kita kelas. Okay, masih tak? Okay. Hopefully you will focus RDQT over DT. RDQT. From based on these two columns only. Two columns only. Because I want you to understand this table. If you understand this table, then you can do the modeling. Okay. LDIT over DT. Okay, thanks. Thank you for the answer. That's correct. Is there any else you can find for the X dot in this table? I would like to call Muhammad Azri Aiman. Is there anything else you can find X dot from these two columns? Muhammad Azri Aiman bin Azahari. Come on, this is only for the first class.
No.
Okay, so what is the answer again? Azri? No, no what? Can you give me a full answer? Azri. No what? Because you will learn how to answer in the presentation and so on. Just give me a proper answer lah, in order for you to practice. Again, Azri, try to answer again with the proper answer.
Only those two?
Once again?
Only those two?
Yes, the answer is only those two. That's correct. Okay. All right. So it means that for you to do the modeling for the electrical systems, okay, electrical system, you just need to refer to these two columns only. Okay, although you have about 5 columns here, you just need to focus these two columns. Okay, and then after that, for sure, your X dot after you refer to these two columns, your X dot for the state space equation here always will be either current for the capacitor. Okay, because the X dot will always be the voltage of the capacitor, and also will be current for the inductor, because IT here refer to the inductor current, so it will be this the first X dot, and then the second X dot will be the voltage for the capacitor VC. So if you see the reference here, the X dot, the X here always refer to current, and also the voltage. I refer to the current of the inductor. You can see current of the inductor, and V is the voltage of the capacitor. Okay, and then after that, do you need to use this formula? Vt equal to 1 over C, the integration of I tau d tau, and also It equal to 1 over L V tau d tau. Do you need to use this equation, this formula? Anyone, you can answer.
No.
No. Why?
No.
Because in this equation, we didn't have any integration, right? We only have the derivation only. Okay, so that's why you must know you only need to use 1, 2, 3, and 4. These four equation, these four formula in order to do the modeling for the electrical system. Okay. All right. So same thing with the mechanical. So we still at the first part. So before we focus on the electrical system, you need to use this table. However, after we discussed just now, we just need to focus on this formula in order to derive the modeling state space system. And then after that, this is a table that you need to refer to model the mechanical system to a state space. Okay, so according to this, you have the first column, first force velocity, and then you have the second column, force displacement, and also the third column, impedance ZMS equal to Fs over Xs. So which column that you think you need to refer in order to do the state space modeling?
Force displacement.
Yes, that's correct. Force displacement. So this is the, only for the your knowledge lah. So actually this is equal. So this thing is equal to this part. This thing is equal to this part. However, you just need to focus on the force displacement formula only. Okay, so this is the remarks lah that you already understand the state space structure here. So I would like to highlight here. So if you can understand this one, so I believe you can do the modeling of the dynamic system on the second part. Okay. So I need to give you an example. So this example I will put in the slide for your reference. So we go to the second part, modeling of the dynamic system. So I need to stop sharing here. Okay, I need to share here. Share screen. Start. Okay. I need to open one thing first. So while waiting for that, okay, this thing. Right. So firstly, come on. So this is the Question. Positive, negative, VT, I, IT, L, and R. Okay. So you can see here.
Doctor, we cannot see the slide.
Not see the slide. Eh?
Yeah.
Yes, doctor, cannot.
Okay, let me try to look at it again. Need to write again. Need to open again this one. You are sharing your screen. Stop sharing again and share again. Start sharing. Start now. Okay, nampak?
Okay, nampak.
Alright. So according to the table, so you have two components here. The first component is R, the second component is L. So according to the formula for the resistor and also for the inductor. Inductor, this one is a symbol. Okay. So we can see that V equal to IR and then I equal to V over R for the resistor. And then for the inductor, I see VL over dt. VL over VIL over dt. Okay. And then also for the current, IM equal to the integration lah. VL, VIL, 1 over M, VL tau d tau. Okay, so this is the thing. So based on this, can you know what is, and then we need to write down the state space equation. X dot equal to AX plus BU. Y equal to CX plus VDU. Okay. So now you only have this information. You are extracting from this question, right? Okay. So you need to determine what is your X dot according to this thing. Anyone would like to try what is your X dot? What is your X dot? You have the resistor and you write down the formula for the resistor, and then you have the inductor, and then you write down the formula for the inductor. Okay, and then you have the state space equation. X dot equal to AX plus BU, Y equal to CX plus DU. Okay, so can you tell me what is your X dot according to this information you have?
VL.
LDIDT.
This one is it?
Yes, doctor.
Okay, so this is your X dot, DIL over dt, or we can say that IL dot. Okay, so do you have anything else? No, is it? Because only this you have the derivative of the parameter. So if you have this one, X dot here as your DIL over dt equal to IL dot, so it means that your X here for sure will be only IL. Okay. If you have IL dot here, okay, IL, sorry, we just go back. You have IL dot equivalent to X dot. So it means that your X will be equal to IL. Is it true?
True.
Okay. So it means that you can write down, and then after that, what is your U input based on the circuit? What is your input?
VT.
VT. So what you can do now is you just write down your information, what you have, your X dot equal to 8X plus BU. Your X dot actually equal to IL dot. Your A, you don't know what is your A. Your X is equal to IL plus B, U equal to VT. So this is how you want to determine your X and your U. Okay, so and then also equal to output Y, the output according to this equation. Okay, so you just write down your output equal to C, your X equal to IL plus D, your input always equal to VT. So your task only need to find what is the A, letter A, B, C, and D matrix value equal to what? Okay. All right. So maybe I can go to the second part. This is my first time using this thing. I have to go to the next slide. Oh, this one. Yeah, that's it. Okay. All right. So this is exercise for you. Yeah. Can you please tell me, or according to this equation, positive, negative. This is R, L, C. I give you this is I, this is C, L, R, V, T. Okay. So can you do the same thing that I showed you before? Can you find X dot equal to AX plus BU, Y equal to CX plus DU? So can you help me to find what is X dot from this circuit? What is X from this circuit? And U this circuit, same thing. Okay, can you help me to extract all the information about what is your state vector from the circuit, what is your input vector from the circuit, and also what your state vector input, your derivative of state vector from the circuit. So as usual, please submit the answer at the WhatsApp group. So I will see the answer from there. To help you to answer this question, I will share you the table. Okay. Plus, need to stop presenting. So I need to put the. Do you still remember the question? Firstly, I give you some time to write down the question. Okay. And after that, I give you some another time for you to see to refer the question, the table. Okay, so this is the question. It's not. Yeah, I need to on it again. Where is the button? Okay. Okay, then. So I will share the table. Share. So you can submit the answer or send answer at the WhatsApp group. Okay, so anyone have tried to solve it or you are stuck with that? Just update me any progress.
Doctor,
Hmm.
dV over dt is equal to what?
Apa dah?
dV over dt.
Okay. What is the question again? DV over DT?
dV over dt is equal to what?
You just put DV over DT ya? Not need to equal to whatever, not need. This one, this is state space. X dot equal to x plus bu, y yt equal to cxt plus dut. Okay, so this is state space question. I need to put it here lah. For easy for reference. Control E. Okay. So okay. So according to the table, this one, okay, you have how many components there? You have 3 components. You have R, you have L, and then you have C. And then there's a voltage equation and current equation. So the voltage equal to V equal to IR. For the current equal to V over R. Okay. Next, we go to the L. L, for the current, for the voltage is what is the voltage equation? For the inductor, LDIL over dt. VL equal to L DIL over dt. So for the current, we don't need to know lah, because is the integration. Okay, and then after that, for the capacitor, so this one we not need to know. Okay, we just need to know IC equal to TVC over dt. Okay, so this is the thing that we have. So now, from 6, we just need to know only 1, this one, 2, 3, and 4. Okay, next we compare to this state space form. So the state space say that you have x dot equal to ax plus bu. So according to this table that we construct, so there are only 2 parameters that can nominate as x dot. The first is, what is it?
DIL over
DIL over dt.
dt.
Okay, equal to. Okay, and then after that you have A. Okay, I need to cancel this one. And then the second is, you can nominate as a x dot DIL over dt dan
dV over dt.
dVc over dt. Okay, so you already collect all the x dot parameters here. You need to put a bracket equal to A. This is A lah, and then the x will be what? Just refer to the first parameter and second parameter. For the x will be here. you just take everything here. If DIL over DT for the X, you just take what?
IL.
IL. The second will be
VC.
VC. Okay, and then plus. We need to continue here. I'm sorry for that. B and then
VT.
VT. Okay, so you can see that from this RLC circuit, R, L, and C, positive, negative, VT, I, R, L, C. You can extract the information. This is, the first is DIL over DT, and second is DVC over DT. So you can say that this also equal to IL dot IL dot and VC dot equal to A IL VC plus B VT. And then the output, Y equation equal to C IL VC plus D VT. Okay, so that's the reason, according to the state space definition, it said that A, B, C, D is the matrices. Okay, so why become matrices? Because of this X dot lah. So let's say in this case, because there are two X dot here, so it will become 2 by 2 matrix. Okay, this one also 2 by 2 matrix. And then this is will be 2 by 1 matrix. And also this one will be 2 by 1 matrix. So let's say if you have more, in this case you have this kind of equation circuit. This is not correct lah. However, let's example this one. So you have one inductor, two capacitors. So every capacitors have different. So in this case, you will have 3 of them. Sorry, I need to cancel this one. Will be A plus B VT. Let's say the input is a VT lah. So you can see that you have inductor. If you have inductor always have IL. Capacitor VC. Inductor IL dot. Capacitor VC dot. So you can straight away, you not need to refer the table again anymore. You have the inductor. So you have IL dot. Okay, you have the first capacitor. You have VC1 dot. And then you have the second capacitor. You have VC2 dot. And then the rest will be IL, VC1, VC2. Okay, and then you have Y, C, IL, VC1, VC2 plus plus D, VT. Okay, so now if you still look at here, if you have two distinct, the matrix here will be 2 by 2. Okay, so how is it about this one? If you have 3 here, 3 derivative of step vectors here, your matrix A will be, what is the dimension of your A matrix?
3 by 3.
3 by 3. 3 by 3 matrix. Okay, so this one will be 3 by 1. This also will be 1 by 3. Yeah. 1 by 3, if I'm not mistaken. Okay, and this one lah. Okay, so so this is the main thing you must know before you start modeling. If you know what's the parameter you want to have here, I believe you can do the modeling easily. Okay, as long as you know what is your target in order to get for the modeling. Okay, so in this case, if you have 2 by 2 here, we call it as a second. We call it as a second order system. Okay, because the matrix A is 2 by 2. Here, because our matrix A is 3 by 3, so we call as a third order system. Okay, similar to this part, this question. This one lah. So what is your what is the order of the system according to this question? Anyone would like to tell me? What is the order of the system?
First order?
Come again?
First order.
That's correct. First order system, easy. Okay. So hopefully you already understand the structure of the state space and also how you want to determine your state vector here, and also to determine your input here, and how you want to determine your state vector here. So in this case, if you are already familiar how to determine these 3 parameters, you can do the modeling, inshallah. Okay. To write here. Okay, what is the question, Osama? Osama, you raise your hand. Is there any question, Osama, or is there any chat? Okay, maybe Osama accidentally clicked the rest up the hand. Okay, so it's okay, Osama, no problem for that. So I will share the attendance link. Copy in the chat box. So you please fill up the attendance from the link below. And then after that, I will wait another 5 minutes. If you have any question, you can ask me. If you didn't have any question, so we will see next week for the modeling example. Okay, how you want to do the modeling, go to the second topic for the chapter. All right, after that, at week number 4, the quiz will be based on the modeling part lah. Okay, modeling part for the class 2nd week and 3rd week. Okay, the quiz one will be on week number 4. You can refer to the teacher plan that I shared in the WhatsApp group. Okay, thank you so much for your attention and also for the response. Good. So just fill up the attendance and I will hear another 5 minutes to answer your question, anything. Okay, thank you so much.
Thank you, Doctor.
Thank you,
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Selamat berpuasa. Oh, I forget to mention that. I will upload the video in the YouTube. So I will share the link in the WhatsApp group. Okay, sama-sama semua.
Thank you, Doctor.
Okay, sama-sama.
Doctor,
Sean.
can I ask if yang susunan X dot tu penting tak?
Dia tak penting.
Dia tak penting ah. Yang
You
mana-mana
can
dulu tak apa.
Tak apa, tak ada masalah.
Oh, okay. Thank you.
Alright, sama-sama. As long as, Sean, the X dot must be at the same line with the X. The corresponding X lah.
Oh, yang nanti yang A tu kena ikut je.
Betul lah, betul tu. So maksudnya the first X dot, katakan IL dot, the first X must be IL. That's the important.
Oh, okay.
Dia tak boleh macam you cannot the first X dot you put IL dot and then the first X you put VC. Cannot lah.
Oh, I see. Okay.
Alright, okay, understand lah?
Okay, yes. Thank you.
Alright. Okay, where you can get the lecture note, I will upload in the Google Classroom. Okay, Akmal, for the lecture note. Okay, thank you for the question. I think there is no question anymore. So thank you again for your attention. Okay, bye-bye. See you next week. Assalamualaikum and have a good day.